This is Magnetism lesson 5, and we're going to do some Faraday and Lenz's law example questions. So first one, if you want to pause and have a go. The magnetic flux through a coil of 5 turns changes uniformly from 18 milliweber to 7 milliweber in 0.5 seconds. What is the magnitude of the EMF inducing the coil due to this change in flux? So EMF is equal to N, change in flux over change in time. So we've got N of 5. Then the change in flux would be the 18 milliweber, so 18 times 10 to the minus 3 Weber, minus 7 times 10 to the minus 3 Weber. And then divide that by 0.5 seconds. And if you put that in your calculator, that will give you an EMF of 0.11 volts, 0.11 volts. That should go okay. Let's move on to the next one. So in this next one, we did this last lesson. I want you to explain on a sheet of paper with no notes, if you can, explain why a magnet, when placed in a copper coil, falls more slowly than it would in air. So you're going to pause and have a go, and then I'll give you the solution again. So let's go through this. So the magnet is dropped into a copper pipe. The falling magnet has its own magnetic field, and it induces a voltage and therefore current in the copper pipe. The current flowing in the copper pipe induces a second magnetic field, and the second magnetic field opposes the original magnetic field that created it. Therefore, the magnet's descent will slow, or it fall at a slower rate, words to that effect. As the magnet slows down, the amount of current produced will diminish. And it will reduce the strength of the second magnetic field, and the magnet will fall at a steady rate once an equilibrium has been set. Hopefully remember that from last lesson, and that went okay. If not, it's just extra practice. Let's move on. So let's pause and have a go at this one, then I'll take you through the answer. So an aircraft of wingspan 75 metres travelling at 200 metres per second cuts the vertical component of the Earth's magnetic field. If the vertical component has a value of 10 microtesla, calculate the value of the EMF set up across the tips of the wings. So kind of a classic question that comes up in exams. So we've got the wings, if you see my expert drawing, like this. So the wingspan is 75 metres. And it flies at 200 metres per second, so if it maps out, 200 metres in a second, so it'll travel 200 metres horizontally. And as you can see, we've got an area, which is 75 metres times 200 metres, which is, coincidentally, 15,000 square metres. So EMF is change in flux over change in time. And the flux is BA, so it's just BA over time. And we've done 1 second. So the EMF is simply BA over T, but for 1 second is just BA. So let's just multiply these numbers. So the magnetic flux density is 10 microtesla. So 10 times 10 to the minus 6 multiplied by the area, 15,000 square metres. Gives an EMF across the wingtips of 0.15 volts. Hopefully that one went okay, you figured that one out. Let's move on to the next one. So let's pause and have a go at this, and then I'll take you through the answer. So a circular coil of diameter 120 millimeters has 750 turns. The plane of the coil is perpendicular to the B field, which is a magnetic field, of uniform flux density 50 millitesla. So question 1, calculate the magnetic flux passing through the coil in this position. So magnetic flux is simply, flux is BA. So we need to do the flux density, so 50 times 10 to the minus 3, multiplied by the area. So we've got a coil, so we need to do the radius squared times pi. So pi times the radius, which is 60 millimeters, so 60 times 10 to the minus 3, and then square that value. So you put that in your calculator, that'll give you a flux that is equal to 5.65 times 10 to the minus 4 Weber. Let's do part 2. So part 2, calculate the magnetic flux linkage passing through the coil in this position. So magnetic flux linkage is just, flux linkage is BAN. So we take the value for the flux that we just got and then multiply it by the number of turns. So it's just the flux which we got is 5.65 times 10 to the minus 4, multiplied by the number of turns, which is 750. And that gives us a flux linkage of 0.424 Weber turns. Let's move on to 3 then. So in 3, the coil is rotated 90 degrees in 90 milliseconds. Now remember, a 90-degree turn will take you, at some point you will be at a maximum, and at some point will be a minimum. So it's just the maximum flux minus 0. So EMF is equal to N change in flux over change in time. So the change in flux is BA times N, which is just the flux linkage from the previous answer, from answer 2, divided by the change in time. So the EMF will be equal to 0.424, that's the flux linkage from part 2, divided by the change in time, 90 milliseconds. So 90 times 10 to the minus 3. So that gives an EMF of 4.71 volts. Then let's finish question 4. Question 4, the coil is rotated 180 degrees. So if the coil is rotated 180 degrees, that means it goes from a maximum flux to 0 flux to a maximum flux in the opposite direction, just like last lesson. So we're going to go from 0.424 Weber turns. Just like last time, we're going to have the exact same value, but in the opposite direction. So the change in flux linkage is these two values subtracted. So 0.424 minus 0.424, which is 0.424 add the 0.424, or times by 2. Then we just need to divide by the time of 150 milliseconds. I'm going to add them, and then divide them by 150 milliseconds, 150 times 10 to the minus 3, which gives us an EMF of 5.65 volts. Hopefully those exam style questions went okay and you found that useful. Thanks for watching. I'll see you at the next one.